Okay, thanks. So this is where we stopped yesterday. We stopped with the example of a non-abelian gauge theory in 4 dimensions, where there was a hope of telling the difference between Higgs and confining phases of the gauge theory using a non-local order parameter, which would be the Wilson loop around vortex-like, global vortex-like excitations. But of course, in that case, we couldn't do a calculation on the confining side because of strong coupling. Let's see if we can change the story and see a different example where we will be able to do a calculation. So this is what I'm going to do. I'm going to compare Higgs and confining phases for a U1 gauge theory. So I'll cook up a model. It's going to be a variation of the abelian Higgs model. And while trying to cook up this model, I'll have to dodge every possibility of phase transition that could rely on symmetry realization or counting of massless modes. So this part is kind of entertaining, as you will see. Doing this with abelian gauge theory will provide me with the kind of control that I need to make precise statements. So here is the example. So I'm going to first talk about the field contents and keep the dimension of space-time that we are in floating for now, and I'll come back to it later. So we start with a theory where I have a gauge field. Okay, it's a U1 gauge field. On top of that, I have some matter content here. So I have a charged scalar, 2 charged scalars. Their charges are opposite. Their charges are +1 and -1. There is also a neutral scalar.
So phi minus star is charged. Those are basically on equal footing, right? Phi minus star has charge +1.
Yes, that's right. Yeah. So I also have a neutral scalar. Now, on top of that, I have the charge fields have a mass, and similarly, the neutral fields have a mass too. And I'm going to drive the charge mass squared from positive to negative values to go from non-Higgs to Higgs phase. Similarly, there are quartic interaction, phi plus to the 4, phi minus to the 4, and phi 0 to the 4. What you should notice here is that I have, so the phi plus and phi minus fields are degenerate with respect to each other, except for the fact that they have opposite charges. So there's actually, you will see that there's a symmetry as a result in the theory. I'll show you which symmetry that is. And on top of that, I have this cubic interaction term that couples phi 0 to phi plus and phi minus. Okay, so now I'm going to discuss the symmetries that this theory has. So first of all, note that all the terms that I've written down, they are all gauge invariant. Even this term is gauge invariant because phi plus and phi minus transform oppositely under gauge transformations. So I have a global symmetry in this theory. It's a U1 global symmetry, and this is the global symmetry that I would want spontaneously broken on both Higgs and the confining side. So this is a symmetry that rotates phi plus and phi minus by the same angle. So phi plus and phi minus have a charge of 1, let's say, under this global symmetry. Phi 0 rotates by twice the same angle in the opposite direction. So this term, this interaction term, is invariant under that symmetry. On top of that, I have a flavor permutation symmetry. This is related to the fact that plus and minus field were degenerate with respect to each other. So I could interchange plus and minus field, and I would have to send the gauge field to negative of itself. And so that's a symmetry of the theory as well.
Or you can interchange plus field with a minus field star. That's not a symmetry? Or maybe your interaction terms break that?
Yeah, the interaction terms will break that, yeah. So now what's the parallel with the example that I discussed yesterday? So first of all, the phi plus and phi minus charge fields are going to be driven from having a wave to a region where they don't have a wave. So I'm going to take from Higgs to non-Higgs regime as I dial parameters. Now the charge field operators are gauge dependent. So they are sort of analog of the n by n matrix valued fields that I had. And on top of that, the product of phi plus and phi minus is gauge invariant, and it carries a U1 global quantum number. This is the parallel with the determinant of the phi. Okay. So that's the comparison. Now, earlier, in order to give determinant of phi a vacuum expectation value, I had coupled it to a neutral scalar and kept it condensed so that it would tilt the potential for determinant. So note that this is what this cubic term is achieving for me. I have coupled phi 0 to phi plus and phi minus. So whenever phi 0 has condensed, phi plus and phi minus together will condense. Although individually phi plus and phi minus don't have to have a wave. Their product will always have a wave. Okay. So that's the story. I want to keep phi naught condensed and vary the charge mass while keeping phi naught condensed. So I'm going to take, so remember, I'm not going to say this later. So yeah, go ahead.
What is MC? Can you show that formula again?
This term.
Okay.
Okay. So I'm yeah.
What about the symmetry that you have talked about? Phi plus going to phi minus star.
Yes.
Phi plus
What breaks it?
I think this term will break it.
it won't remain invariant. Need to add something.
But let's check that quickly. So that's phi 1.
Yes.
Suppose I give all my fields charge 1.
This goes to
Right.
So it's phi 1, phi 2 star,
Yes.
phi naught, plus phi 1 star, phi 2, phi naught. That's the HC.
So this term is phi plus, phi minus, phi plus star, phi minus star, phi 0 star.
Yeah.
So
Phi 0 is real, right?
it's a complex.
Because it's charged under the new one. Yeah,
It's
yeah,
charged.
yeah. Okay.
Oh,
That's that.
It's a boson.
Yeah. It's a complex.
It's a complex boson. And so this is the charge mass square, and as I drive it from positive to negative values, I'm going to go from non-Higgs to the Higgs side, okay? And there's a reason I'm calling it
Phi naught
non-Higgs.
is always going to be negative.
Yes, that's right. So this M0 square is always going to be negative.
And so the distinction is going to be whether phi plus and phi minus are individually condensed or not.
Exactly.
So either
Yes.
you have only a pair condensate or you have a condensate at the individual pair.
Right.
And
Exactly.
these are of course distinct phases.
Well, you will see that yeah.
Yes, but no, but that's okay. We know how to make. We know that you're going to get condensates of something that are charged. That's not a problem.
No, but this is the danger, right? Because
Yeah.
the thing that looks like a gauge non-invariant guy condensing may not be distinguished from it not condensing.
Right.
That's the Higgs confinement.
No, I understand, but in this case it's plus and minus.
No, in this case, phi plus is itself gauge dependent.
Yes.
Phi minus is also
Yes.
gauge dependent. So I can't use their waves alone
Not
to
their
tell.
waves, but yeah.
Okay. So yeah, I'm going to drive parameter from one regime to the other while keeping phi 0 and phi plus phi minus condensed in both sides. So, however, there's obviously a phase transition in 4 dimensions, so that's not going to work. Why? Because it's the Wheelian-Higgs model. Okay. So how do you know? You can just count the number of gapless modes. In the Higgs side, your photon is going to be gapped because of the Meissner mechanism. On the other side, the photon is just gapless. Okay, it's ordinary Maxwell theory coupled to some heavy scalar fields. So on top of that, there's also no confinement in 4 dimensions. Okay, if I just look at the Maxwell theory. So I'm going to try to dodge this by going to 2 plus 1 dimensions. Okay. So
Sorry, just to get orientation again. So in the side where it's Higgs, you've got no massless photon,
that's right.
and the side where it's Higgs, you have a massless photon. That's your point.
In
Sorry,
non-Higgs,
unhinged.
yeah, unhinged, yes.
Yes, you have a massless photon.
Yes.
That's your.
Yes.
That's your.
So you have to jump that hoop and do something to your theory so that you get rid of the massless photon on the unhinged side. I just wanted to make it non-trivial, like the statement that eventually the statement that I'm going to make, I want to make it non-trivial. That's why I'm trying to get rid of all the possible phase transitions you would have guessed by looking at, Landau paradigm or.
Well, in your example from yesterday, on both sides, the gluon was massive.
Yeah.
One due to Higgsing, one due to confinement.
Yes.
Is that an analog of that?
That's what I'm trying to cook up, right? So in 4 dimensions, there is no analog. So I will try to do it in 3 dimensions because of that.
Okay.
So
Because you're dealing with U1, you're saying, right?
yes.
Yeah.
So if I write down an abelian theory in 2 plus 1 dimensions, in general, it can have a massless photon. If I look at the potential between two charged objects in 2 plus 1 dimension, the Coulomb potential is going to be logarithmic in distance. So what do I want to do? I want a linear potential, first of all, between charge fields. More importantly, I will need to gap out the gauge boson. Okay, and you will see that these two are going to be related to each other. Okay. So this is the procedure that I do. So it will come in the next slide. So as I said, in 2 plus 1 dimension, you can have a massless photon. So the kinetic term, Maxwell kinetic term, looks like this. So one way to think about this is to write the massless photon or the gauge field in terms of the dual photon. So that's what I have done here. Sigma is the dual photon field. And now the kinetic term, Maxwell kinetic term, you can write it as a kinetic term for the dual photon field. And if you look at it, look here, you can see that this term, this kinetic term, is actually invariant under shift symmetry. So sigma can be taken to sigma plus alpha. And so this term is invariant under that symmetry transformation. And it's called magnetic topological symmetry in 2 plus 1 dimensions.
Now, because you are in 2 plus 1 dimension, you can use Polyakov mechanism.
Yeah, that's what is going on eventually.
You can use Polyakov mechanism, and then you can understand confinement. And so the only part that will change is the part which is not Higgsed. The part which was Higgsed is still massive.
Yep.
The part which is not Higgsed, earlier it was massless.
Yeah.
So that will be massive because of Polyakov mechanism.
Yes. Okay. So before you do the Polyakov mechanism, sigma, the dual photon, is the Goldstone boson of U1 topological symmetry spontaneously breaking. But now, what you can do is that you can take the abelian model and UV complete it using either an SU2 gauge theory, or you can UV complete it on lattice. In both cases, what happens is that you now have finite action solutions, as he was talking about. These are monopole instantons, and they induce a mass for the photon. Okay? And the mass term looks like this. So now the photon is gapped, and the vacuum is invariant under all symmetries. So what have I done? I have eliminated all apparent symmetry-driven reasons to expect a phase transition. Okay. According to the Landau paradigm, there is no reason to expect a phase transition. But of course, there is life beyond Landau paradigm. So as a result, what I'm going to do is what I suggested yesterday, is that I'm going to compute Wilson loops around vortex-like excitations.
So on both sides there is no photon.
Both sides there is no photon. Yeah, on one side it's not there because of confinement, on the other because of Meissner.
Side means whether the thing has condensed or not?
Side means, yeah, on one side you have the Higgsing going on, and then I have driven parameters to go to a regime where there is no Higgsing.
So this driving is happening with MC.
MC square, yes.
MC square.
Yes.
With a negative.
Yeah. So everything you said would work at the moment just for one charged field, right?
What do you mean?
You don't need all the bells and whistles you had for this description. U1 coupled to one charged field,
Yes,
both sides.
right.
But then there's no transition.
There is, yeah, yeah, that's right.
Whereas here
Yeah.
she's somehow going to have.
Yeah.
And actually, just remind me of something else. I mean, this is isn't this the theory that is supposed to be dual to dual to just Wilson Fisher?
Yeah.
So
Charge.
that's one of them, for one of them.
One charge superfluid is dual to 3dxy.
Right,
Now she's
right.
got two charge superfluids coupled to the same A, and they have opposite charges.
Yeah.
So I don't know how the duality.
So find the dual. Okay, that's the thing to do.
But
Project.
But hang on, but just let's go back to the one field.
Yes.
On the dual side, in the symmetric broken phase, there's definitely a Goldstone boson.
Yeah, there is a transition there.
Boson is a photon.
That's the photon.
But
Yeah.
I thought you were saying the photon was gapped in both phases. That's what's confusing.
No. Here it is
No.
one phase
No,
is
no, no.
gapped because
Okay.
it's Higgs.
So in the when
And
there's
in
no
other case, when it is not
When
Higgs,
there's
it
no
is gapped because of
condensation.
confinement.
No, but I'm
Yeah.
asking how that
In
fits
the
with
absence
dual
of
and
confinement, there is a transition.
So what do you mean in the absence of transition?
Well, you have to. I UV completed it with this SU2 theory. You don't have to do it. It's UV complete anyway, right? It's 2 plus 1
suppress the
dimensions.
monopole operators and then this duality works. Oh, I understand. So you're saying that if you make this not a U1 gauge theory,
Right.
but an R gauge theory,
Right. Right.
then the
Yeah.
duality works.
Yeah.
The
Yeah.
duality doesn't
Yeah.
work without reason.
Right.
Okay, so I should not think of this as dual to, even with one guy. The physics you're talking about is not dual to Wilson Fisher.
only if it's curl.
Yeah, that's right. That's right. Yeah, that's right.
Because that has completely different physics. That has a massless mode.
Yeah.
And you're saying it doesn't have massless.
Right. Right.
Okay.
Yeah.
If you put in the cosine curl, I think you get an anisotropy in the 3dxy model, which then kills the.
Right. Right.
So then again it's massive.
Yeah. So I don't know. So I think what you're saying is, if I UV complete this with a lattice theory.
I think there is a version.
Oh, okay. Okay.
Yeah. You can, on the lattice, you can just by hand suppress monopoles, right?
Right. Right.
Put a monopole operator, give it a high mass.
Yeah.
That will kill. Yeah.
Yeah.
So there is a clear question if you should include monopoles in path integral or not. So you need to understand if they are smooth configurations or not.
Right.
In a strict sense.
Right.
And that will depend on if your U1 is compact or not.
Correct.
Right.
Exactly.
Right.
So, but the physics that she's talking about is not, even with one field, is not dual to the
Right.
Wilson Fisher.
Because she's always worrying.
She wants
Yeah.
it to be mass.
Yeah.
She wants it to be gapped. at
Yeah.
the
I
end.
want. Yeah. That's right.
And the other side has a gapless phase.
That's right. Yep. Yep.
The other side with cosine curl to do it.
With cosine curl, sorry, what would that be in the
See,
scalar
instead
sense?
of curl A square, I do cosine curl A.
Uh-huh.
The curl A square gives a 3dxy.
Okay.
My guess is if you do cosine curl A, you get 3dxy plus anisotropy.
Plus anisotropy. Okay, fine.
And anisotropy kills the spin waves.
Sounds great.
Everything is good.
Sounds great. Sounds great. Sounds great. But it's just that I shouldn't think of it like
No.
Mhm.
like the 3dxy.
Right.
Yeah.
Even if you have compact U1s, the one for which your particle vertex duality will work for single. In this case, there is a non-trivial coupling.
Non-compact.
No, yeah.
Non-compact.
Yeah,
that's what
non-compact.
we got it.
That's the one.
Right,
You
right,
have
right.
the
Correct.
So
Yeah.
the one for which the particle vertex duality will work.
Is non-compact.
Even if you take that,
Non-compact.
let's take. I am totally not sure.
You may
It
just
is
have
non-compact.
checked.
Yeah, it is
non-compact.
Okay, I have to check this statement.
You can check it.
So with that, even if you try to write this model, there is a non-trivial interaction between these two. So it's not clear that how this duality will work.
No.
Okay. So let me go into computing the Wilson loops. So I'm going to do this in the Higgs regime first. So let's focus on this term. So when I'm in the Higgs regime, MC square is negative. They have condensed, like phi plus and phi minus have condensed. Phi 0 has also condensed. By the way, I should have mentioned here. So because you're in 2 plus 1 dimension, your coupling has a dimension. So E square is dimension full. So when I'm dialing parameters, it's really MC square over e to the 4 is what I'm dialing from very positive to very negative values. And it's really when MC square is much greater than e to the 4 that I really have control. So that's where, both in the Higgs and the in the confining side, I have to go deep in those two sides to get control. So these fields are condensed. Now the only thing that's remaining to look at is this term. So what happens is that when you're looking at a certain size system, the energy density corresponding to this term scales as the size of the system. So you better minimize this term to get what the effective potential is. So this locks the phase of phi 0 with phi plus and phi minus. So let's say phi 0, now I'm looking at vortex-like solutions. So phi 0 is winding around a point in space with e to the I theta. So that's a vortex. Now this will ensure that phi plus, phi minus together wind as e to the minus I theta, just to minimize this term. Okay. As a result, what is going to happen is that either phi plus is going to wind as v e to the minus I theta, and phi minus is not going to wind, or the other way. And this is again simply because you want single valuedness for the wave functions. So it cannot be that parts of the winding is carried by one field and another part is being carried by another. Everything has to be carried by either phi plus or phi minus. So now I want to find out what the holonomy or the Wilson loop is. So I need to know what the gauge field is doing far away from the core of the vortex. So I have to write sort of an effective potential for the gauge field. And the way to do it now is to look at the kinetic terms for plus minus fields.
Sorry, I was spacing in the last 2 minutes. So you're now in the Higgs, deep in the Higgs phase?
Yep.
So all your analysis is classical?
Yes.
Okay. And please could you just repeat one? You both phi plus and phi minus are condensed?
Yes, and they are winding because of this term. Okay. So this you have to minimize this term because its energy, the corresponding.
Winding in the presence of sorry, winding.
So phi 0, I am putting in a winding for phi 0. As a result, phi plus, phi minus together have to wind because of this term.
I see. So all three fields are condensed in your
Yep.
phi 0, phi plus, and phi minus.
Yep.
Okay.
Yep. Yep.
Phi 0 has charge 2, phi plus and phi minus have charge 1.
Yes. Yes.
Okay.
Under the global symmetry. Yes.
Under global
Yeah.
symmetry, yes.
And they. Yeah. Go ahead.
Firstly, just winding mode of phi 0 has finite energy or not?
No, it's so these are again global superfluid vortices. Okay.
Right.
So they have logarithmic energy, logarithmic divergence in energy per unit length.
But I was thinking that gauge field.
No, but there's a d mu phi naught square that doesn't get killed by gauge field.
Not only that this doesn't get killed, even these two together won't get killed. You
One
will
of
see
them
that.
will get killed, the other one.
One of them will get killed half.
Half.
Yeah, yeah.
I see. So you said that if I choose the gauge field to kill the winding infinite energy in phi naught, it will induce infinite winding energy in phi plus.
No way of doing it.
Yeah,
Yeah,
you
you
can't use. Yeah.
Firstly, phi naught is not charged. Right?
Yeah.
What am I saying?
You can't do anything.
You can't do anything.
Yeah, yeah,
The
yeah.
other one, if you do it for one, the other one gets screwed.
Yeah,
Yeah,
yeah, yeah.
That one is minus
Because the
one.
global charges and the gauge charges are opposite.
Right,
So
right,
current
right.
flows in different directions.
Yeah.
Yeah, yeah. So the kinetic term for the gauge field is not going to matter because there's Meissner effect for it, so its energy doesn't scale with the volume. These terms are, again, as I said, their energies are logarithmically divergent. As soon as you put in e to the I theta kind of an ansatz for these fields, you can compute it, the energies in cylindrical coordinates, and you will see that there's logarithmic divergence, so better minimize the energy density corresponding to these terms. And so that's what I'm going to do, and you have already guessed what's going to happen. So what I'm doing here is I'm parametrizing the gauge field in terms of the Wilson loop. So I write the Wilson loop as an e to the I times an angle, and then now I write the energy density corresponding to the kinetic terms in terms of that angle instead of writing it in terms of the gauge field. Right. And so this 1 over r square is coming from the fact that I was writing this effective potential in cylindrical coordinates.
I'm sorry.
Go
You
ahead.
said this, but you said phi naught winds, let's say, once.
Yes.
And why again did phi plus and phi minus also have to wind?
So it's because of this term, okay? Otherwise your energy will be infinite. It will scale with the volume. So you better minimize this.
So you're saying there's a vortex
There, yeah, both of them are.
But in terms
Uh,
of the current configuration, one
yes,
of them
yes,
is
yes,
not
yes.
there.
Yeah.
You said the way to make that term minimum is to make phi plus phi minus phi 0 real.
Yes.
Yeah.
And therefore, if phi naught winds with the phase, phi
Yeah.
plus and phi minus together have to wind with the
Mm-hmm.
opposite phase.
Yes, yes.
And so if phi naught has winding 1,
Right.
then you can compensate that by phi plus and phi minus each having winding minus 1. Because they have
Together having winding -1.
together having winding minus 1.
Yeah, you can't have half.
Yeah.
But phi naught is charged 2, right? Under the global symmetry.
Yes.
Whereas phi plus and
Phi
phi
naught
minus
is not charged.
It's not charged.
under the global symmetry.
Under the global.
Under the global symmetry it has charge, and this winding vortex is under global symmetry.
Yes. Yes.
So a single winding
Mhm.
of phi naught
Yes.
is like 2 windings of phi plus, right?
Mm-hmm. No.
Phi- Just look at that, no? It's phi plus phi naught. E to the I theta and phi naught is e to the minus I theta and phi plus or in phi minus.
Why is this related to charge under global symmetry?
Yeah, this is actually
It's
not related. Yeah.
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 Okay. Thank you.
Yeah.
Thank you.
Yeah.
Similarly.
Right.
But between phi
But
plus
if
and
I
phi
don't
minus.
do that,
Yeah.
if I say phi plus and phi naught not winding, only phi plus and phi minus and only phi naught winding,
Okay.
then that term will have a winding.
That term will have a winding, and it'll cost you a lot of energy.
Yeah, but isn't
Why
this
would it cost me a lot of energy? There's no gradient here.
So there's going to be a cosine theta here. So if you write this, so e to the I theta, right?
Yeah.
So it's going to be some constant times cosine theta,
Yes.
right?
Yes.
And
But
so-
integrate cosine theta over the space.
Yes. So it's going to be L cubed, right?
Yeah, it's just magnitude of cosine theta, you want to make it maximum.
Okay.
So theta becomes
you
1.
use some extra.
Yeah.
Yeah.
You want to minimize that.
Minimize that.
Right.
The magnitude of phi plus and phi minus is fixed by the potential.
Right.
Yeah,
Right.
yeah.
Right.
So that you
So the best thing you can
do is get the phase real.
Yeah.
Wait, now is this vortex, can I think of this vortex like doing a symmetry, global symmetry transformation around the point and rotating that?
I'm not.
That's not how you think.
No, I don't think of it like that.
But that would anyway cancel the phases, right?
So-
Because if you do the same symmetry transformation on phi naught
Yes.
and on phi plus and phi minus, the fact that the whole thing is neutral will cancel.
So
the
this is not
Opposite.
quite a symmetry transformation, right? What I have done here. So the answers that you see here.
It
Oh, you
would be if you make phi, if you put a 2 with phi naught,
yes.
-1 with plus phi and -1 with minus 1.
That's also something.
Oh, yes. You could do that. You could do that.
And
Yes.
that is not the minimum minimum
That's a different kind of work.
That's a different kind of a word.
Somehow I would suspect that's minimum energy because it's related to symmetry.
You are right. That's
Hmm.
that has zero energy, but that is not something that can distinguish one from the other.
Okay,
So I don't care about that. Okay.
Okay.
That's also a vortex. It's very
Yeah.
negative.
Yes.
Yeah.
So the Z2 that gets broken is the flavor permutation kind of thing.
Yes. Yeah. That's right.
Okay, so but just to get your vortex in my head, you're winding phi naught with one
winding.
and phi plus with -1 winding.
That's
or phi
right.
minus with
That's
winding.
right.
How is the one, wait, phi plus with the same winding and so in your case phi plus winds, phi minus doesn't or the other way around,
Yeah.
right?
That's right.
What Shiraz was saying is both wind in the same way.
And phi naught winds twice.
Phi naught winds
Right,
twice.
but if both wind in the same way,
Yes.
then you can't use any gauge field configuration to screen out
Yeah.
of both, so you will actually get
A is equal to 0. Yeah, but even here you're getting log
for a
I
different
have.
reason.
Yeah. So
So I'm not sure which one's lower than the other.
so let's see.
But you can consider any
I
one.
think.
Yeah, you can consider it, but they both seem to diverge the pair.
What is the minimum of this?
Sorry, what did you
So, okay, hang on. Yeah, so you want phi plus to wind as e to the minus I theta, phi minus to wind as e to the minus I theta, and phi 0 to wind as e to the 2I theta,
Yes.
right?
Yeah.
So this is not going to contribute at all to what the gauge field does.
Yes.
Only these two are going to.
Correct.
So here I have plus 2 pi plus alpha, and this one is,
You can completely
right?
cancel. Oh no, if
You see, you can't do
because,
this.
yeah.
You're going to get a log either way.
Right, right.
So why is this lower in energy? I don't know.
So the one that I wrote down
Yeah.
didn't have this 2 pi, this was 0.
Which one?
This
Yeah.
was like, this
Correct.
one was
One
not
of them was
winding.
0, the other was 2.
Right.
Yes.
And as a result, alpha was pi, right?
Alpha was
Pi for this one,
to
right?
halve them both.
I actually didn't even say that in the talk. We are now going ahead, we are skipping ahead.
Yeah.
to do what? To
She halves them both, right? She'll get half square plus half square instead of 1 square
Yeah.
by making it.
Yeah, so if I try to minimize this, right, I get alpha equals pi,
Yes.
right?
Yes,
And then I
to half both.
plug in here, and that gives me a finite number over r square, and that would give logarithmical divergence.
Yeah, I agree with you that. If we're getting 3 by 2 here, we get 5 there.
Yeah, this is low.
I agree. Maybe 6. Because 2 square plus 1 square plus 1 square.
Yeah, exactly.
Phi
So-
naught we get 2 square, because phi naught can't be cancelled by gauge field.
Right, phi naught is,
Why not to pull down? Yes, that's giving you.
No, no. We're comparing with what I was saying.
Yeah.
No, this was that 2 pi plus alpha.
on top of that there is this one also, which I haven't written.
What she said is there in the on the
Plus 2 pi the whole thing square.
That is always
Because
there.
phi naught can't.
Right, right.
Now, this
Here
will be
actually, hang
minimized
on,
by
this is actually 4 pi.
4 pi. 4 pi.
Yeah.
Yeah.
So therefore,
Four,
we're
yeah.
drawing all 2 pi's, it's 4 plus 1 plus 1.
4 plus 1, exactly. 4 plus 1.
Right,
That's one.
right,
So
right.
6.
That's bigger.
That's big.
That's bigger.
Yeah.
And the other one will give 1 from phi naught
And
Yeah.
plus half square plus half square. So 3 by 2.
Three
So
by
6 versus 3 by 2. So huge.
Right, right.
this is the lower energy.
Yeah. Okay. So, okay. So now you can compute the Wilson loop and you get -1. So what this means is that these vortices, these superfluid vortices, carry magnetic fields in their core. Okay. So now I want to know what happens on the non-Higgs side, which is why I'm doing this calculation in the first place. Okay, so that I can do this calculation under control. So I'm going to a region where mc square is much bigger than e to the 4, so it's very positive. So what can you do in this case? You can, the charge fields are heavy, so you can integrate them out from your theory in principle. And you might think, okay, so what you have is a neutral superfluid and an uncoupled electromagnetic sector. They won't talk to each other, and so you shouldn't have a magnetic field inside the core of a vortex. But phi 0 can couple to electromagnetism via its coupling through the heavy charge fields, right? So what I have to do to answer the question I'm asking is to write down an effective field theory that couples phi 0 to the electromagnetic sector.
Sorry, what is the question asking?
So what happens to the holonomy? So I computed it on the Higgs side, and now I want to do it on the non-Higgs side or the confining side.
What did you compute? The Higgs side, there was this vortex, and I missed the punchline.
Yes, the holonomy is -1.
Holonomy of what, please?
The gauge field.
Just because this is what minimize the
This
energy.
is what
Yes,
minimizes
yes,
it.
yes,
Okay.
yes.
Yes.
And so I want to compute the Wilson loop on
So
the
this
confined
holonomy,
set.
this holonomy is what fixes how much magnetic field is being
Yes, yes.
by the
Yeah, it's a way of detecting that, right? So it's really an Aharonov-Bohm phase corresponding to that.
So how much magnetic field is in the core of it?
Yeah. Yep.
The minimum energy.
Yeah.
Now you're going to go to a regime where mc square is large and positive.
Yes. Yes. And then ask the same question.
In that case, there is no such vortex exists, right?
Which
The
phase?
vortex doesn't exist.
Which phase?
5 plus and 5 minus are not condensed. Then.
5 plus and 5 minus are not condensed, but
Phi
phi 0
zero
is still.
is still, I see.
And as a
There is
result,
no magnetic field.
you
So
would
you have
think,
to
you
use
would
would
think, you would
But
think.
it does.
There is, I mean, eventually I'm going to say that there isn't, but
Okay, good.
you have to be careful to
Alright,
get
alright.
there. Okay?
So your distinction then is going to be vortex carries magnetic field versus vortex doesn't.
Right, right, right. And the way I'm detecting it is via this Aharonov-Bohm phases.
Yes.
Okay.
What mass is taken to positive?
The charge mass squared.
That's
Right.
And
So
when
this.
you say Aharonov-Bohm phase, you mean just the Wilson line around this.
Yeah, yeah, yep, yep. So now I'm going to write down the effective field theory that couples phi naught to gauge field. Okay.
I'm sorry. Hassel,
That's
but you say MC square is large, and it's therefore you say it doesn't look like, at least classically, phi plus and phi minus themselves have a wave.
Yeah.
That's right.
But you argue that in some sense phi plus phi minus always have a wave. Yeah. That will continue to be true, yeah?
Phi plus phi minus together
No,
will have a
composite
wave.
operator.
Yep,
There is
yep,
always condense.
that's right.
Mm.
This term is going to force that to happen.
Yeah.
But the point of this thing, the gauge field becoming half, was that phi plus and phi minus themselves had a wave.
Exactly.
Correct.
Yep. So it's a gauge invariant way of detecting the fact that you have a gauge dependent macroscopic wave function. Okay.
Yeah.
So that's what I'm trying to
Yeah.
do.
But this analysis is for much large values of MC.
Yes.
There could be phase transition as you lower MC for, as you go through the origin, there could be several phase transitions.
That's what I'm trying to prove to you,
When
right?
do, there's at least one.
Yeah.
Right, so the analysis from this part will be only in the asymptotically large sector.
But
Yes.
it already proves there's got to be one transition, no?
That's right. That's
the
right.
point.
I'm trying to prove that.
That's
Okay.
the point.
Yeah. Okay. So now I want to write down the effective field theory. Now when you want to write down an effective field theory, you should keep in mind the symmetries you had in the UV theory. So this is the most relevant one actually. So I have a symmetry that changes, that interchanges phi plus with phi minus and A going to minus A. So that's my flavor permutation symmetry.
Sorry, just if you don't mind, I just want to understand the theory you're talking about a little. So is it a flow from, are you thinking of it like a well-defined field theory defined all the way to the UV? Or that's not important?
I think it is, yeah.
It is, okay, good. So the theory is defined in the UV with, as a free theory, and then there's a flow,
Mm-hmm.
starting with these 5 operators.
Right.
And in the absence of the gauge field, this is what would either go to a massive theory or Switzer-Fisher
Mm-hmm.
theory.
Right.
Okay,
So
yeah.
I'll probably discuss the UV completion tomorrow,
Okay.
but let's see how
Okay.
far I can get. It's going to be an SU2 gauge theory and then standard stuff. So this is my flavor permutation symmetry. When I integrate it out, integrate the phi plus and phi minus out, what I'm left with is A going to minus A. So that's one of the symmetries of my effective field theory. Okay.
Sorry, this is the symmetry that is broken.
This symmetry is no.
Why is this
Spontaneously broken in the other side.
In the
That's-
other side.
So you already,
This symmetry is not spontaneously broken.
No, it's not. Because both vortices exist and have equal mass, equal energy, no? Either you wind in phi minus or you wind in phi plus.
Right, they have the same energy.
So this symmetry just interchanges one type of vortex to the other type.
Right.
Okay. It just, this symmetry predicts that there will
Right.
be two kinds of vortices with the same energy.
Right.
Each one of the vortices has a configuration which breaks the symmetry, but there is a pair.
Yeah, so
Yeah.
it's like saying there are two states and one state transforms to the other.
Right.
not a vacuum state.
Yeah, not the vacuum.
So now note that phi 0 is neutral, so it cannot couple to the gauge field directly, so it has to couple to the field strength tensor, okay, gauge invariant operators. So these are some of the terms that you can write down in your effective field theory. So these are the standard terms that I started with for the phi naught field. This is m naught square, that's a typo, and the lambda phi to the 4 term, and these are the interaction terms. These are some of the interaction terms that you can write down. Now,
So what prohibited odd terms? Sorry.
yeah, so that is this symmetry, but you're sort of, you're skipping ahead.
Okay.
So I was going to make a big suspense about, there could be odd terms and what you could get as a result. But
Okay.
this
What
term
about
is
chance
really
circumstance
is going to prevent you from having odd.
So A goes to minus A prevents odd terms?
What about Chance-Simons kind of terms?
That there's a parity
So by
symmetry
way,
here.
yeah.
That's assumed.
Understand.
So go ahead.
So I meant odd in phi naught.
Oh,
Yeah.
okay. Odd in phi naught.
What's ruling that out? Something elementary which I'm missing.
So what kind of term? Oh, you want phi naught cubed, let's say.
The U1 symmetry will do it.
U1
U1
global
symmetry.
U1.
Yes.
Global U1, yes. So okay.
Why are you getting F mu without any suppression of MC? I thought that you were integrating out.
You are getting suppression of MC. I just haven't written down.
Yes, higher orders probably AB and so on.
Yeah.
Why not the leading order term? Oh, leading order was just the kinetic term.
Yeah,
I see.
yeah.
Just
I haven't
These
written
are
those
all
down.
1 by mc square.
Right.
Okay.
So the first term that you see here, this actually describes Rayleigh scattering. Okay, so you know that in atmosphere you have atoms, and they scatter photon, and why the sky is blue is explained by this term. Okay, this term is not going to be useful for me, but it's just something curious that I wanted to point out. So here, as you see, only even powers of f appear.
This
Okay.
capital F on this slide is the same as small f, right?
Yeah.
Previous slides.
Yes. So could you write a term that would couple the vortex configurations in phi naught with the gauge field, such a way that you could get a magnetic field? So in general, you could write such a term, and let me write that term. So it's a term like this. Okay, so it's an antisymmetric derivative of phi naught star and phi naught coupling to f mu nu. Okay. So in general, if you were to have a magnetic field inside the core of a vortex, it would cost you some energy, but this term could lower the energy. And how would you see that? So one thing you can do is to plug in your vortex ansatz in here. It's a static configuration, so all the time derivatives are 0. So this is practically a coupling between magnetic field and the vortex. Okay, like the vorticity.
You are considering same kind of vertex that you are considering on the other side?
Yes. Phi naught going as e to the I theta. Okay.
And only one of them is rotating and the other one is fixed between phi plus and phi minus?
These don't have webs now, so they don't wind. Phi plus phi minus together will rotate, will have a winding, but
Right. That's not it, because that is indicated out.
yeah. So in principle, you could have this coupling between magnetic field and vortex, and there is something interesting here related to superfluid helium, which I won't talk about here, but that's also something we figured out while trying to think about this project. So anyway, so in principle, this term could lower your energy. This corresponds to a current of this form. Okay, so what you can do is take this term, integrate by parts, take the derivative to hit this term. So you will get a coupling of A mu with.
So this term does exist.
Yeah, this term does exist, and if you plug it.
You have an external magnetic.
What do you mean?
You apply a field. This term doesn't, but if I break your A2 minus asymmetry by just saying I apply external magnetic field.
Well, you could break the symmetry in other ways too, right?
If
You could.
I apply an external magnetic field, this term can exist.
Uh,
in phi naught.
when you have the symmetry in your UV theory,
Yeah.
I don't think it can exist.
Yeah, no, I understand, but I'm saying now I just apply, so I have the sample, I apply external magnetic curl A, I just set curl A to something.
Right.
Turn on.
Right.
I put a solenoid there.
Yes.
Then this term will exist.
No, I don't think so. So it's because of the fact that you only have even
No,
parts
but
of
I'm
it.
saying now if I put an external magnetic field, I explicitly broken the A2 minus.
Oh.
Right?
No, I don't think that's going to do it. So
The Lagrangian with some background field.
Yeah.
right, you
Lagrangian to begin with didn't have all.
That's correct.
so the way phi plus will couple to the gauge field, your
Yes.
external field, will be the same as how phi minus couples.
Also, they'll cancel out.
They'll cancel. That's the point. Yeah.
They'll always cancel. They won't generate this term of phi naught.
Exactly. They won't.
I see.
And so this is a result of the fact that you have this symmetry. Okay. So that's why they will exactly cancel. If you did have this, if you break their charge mass square, if you change their, one of the fields had different mass compared to the other.
Plus 2 minus symmetry if you break them.
Yes. You break the Z2. I have a Z2, right. So then, so in general, you could write such a term, but you can't in this example. Okay. So as a result, you don't have any magnetic field in the core of the vortex. And so now the Wilson loop or the holonomy is strictly 1 thanks to the flavor flip symmetry that I have, or flavor permutation symmetry. So now I'm going to compare with the Higgs side, and you have already guessed the answer. So this is the very positive mass squared side, the Wilson loop is strictly 1. On the negative mass squared side, it's strictly -1. So there has to be a transition, at least one transition. This could happen where, you know, the two just jump at one point. Okay, I mean, there's going to be a point where it could just start moving away from 1 or -1. That's where you could also have a transition. It's just a most obvious picture that I could draw.
I didn't quite understand -1 and 1. What is the sign?
Sorry?
So this is e to the 2 pi I alpha. I mean e to the I alpha.
Right.
Yeah.
Yeah.
Phase
It's
zero.
the
A equal to pi versus the, and that was 1 y. So on the Higgs side there is -1, okay, and that was
because
one-
there's no
Alpha
magnetic
there is
field.
no
is-
holonomy, there's no
Nothing.
magnetic field.
Yeah.
It's the phase of the winding.
So if I was just to play devil's, this sounds completely reasonable, but if I was to play devil's advocate, your calculations are really valid, asymptotically there
Yes.
and asymptotically there.
Yes.
Now, though it would be strange, how do I know that it isn't a smooth curve that goes from minus one to
Yeah. So the way to do it is to compute the quantum corrections, and that I won't show you.
But that you can only do in a power series in 1 by n, right?
Yeah, you can do it.
But unless you go to all orders in 1 by n, how can you show that?
You can find out what the form of the effective potential is.
To all orders in 1 by n.
Yes. From the symmetries that you have, you can
So you
take.
say the symmetry-based argument that tells you that in a finite range,
Yep, yeah.
in the 1 over m expansion,
Yes.
this is exactly 1.
Exactly, that's
And
the point.
Symmetry-based argument that tells you in a finite range in 1 over m expansion,
Yes.
that's exactly minus 1.
Yes,
And then you
yes, yes,
Sorry, I didn't understand. So on the Higgs side there were two states at that energy.
yes,
The one with a pi plus and the one with a minus.
Yes.
Pi minus.
Yes.
Now what is the two states corresponding to that vortex?
So you won't be able to tell by looking at the holonomy or the Wilson loop. They'll both have, they'll have the same holonomy on the two sides. Sorry, this is the state I'm pointing to. So both of them will have.
No, I understand. In the Higgs case, there is degeneracy,
Yeah.
right? And that degeneracy is gone
Yes.
on this other side.
Yeah, there's
Well, you is
There's
still
phi naught winds and phi plus and phi minus.
don't wind. So it's
Yes, but isn't that an indication of something drastic happening?
well. This is it, right?
Yeah, I mean, this would bypass this objection of
Difficult.
this continuously happening, right? This one state becoming two states.
Well, I don't know if you can call it one state becoming two state.
Whatever, right? I mean, in the states in the winding, the first winding sector of phi,
Mhm.
the lowest energy states in the first winding sector of phi. On this side there are two. On this side, I don't know. Seems like there is one.
No,
I'm
but
asking if there is another one.
So I guess what Shiraz was saying would be that you have some magnetic field in both vortices on the left, and that magnetic field gets smaller and smaller and smaller and goes to zero.
Yeah, you could imagine that happening. That's right. And right,
I don't know. I'm just saying Shiraz was.
yeah,
I mean, it never sounded plausible, but I was just trying to
right.
check what we've actually shown.
Yeah, that's right.
But can I ask one question about picking this out?
Yes.
If this is at zero temperature. In the
Yeah.
sense of actual temperature.
Yes.
2 plus 1d, where the plus 1 is infinity.
Right.
It's not finite. Now if I do non-zero temperature,
Right.
presumably you've gone from a regime where you have this phi naught superfluid,
Yes.
which can have a Pascal's phase,
Yeah.
to a phi naught superfluid that cannot.
I suppose
It cannot.
Cannot.
Why do you say
Because
that?
on one side,
Yes.
the phi naught superfluid has both have logarithmic.
Both have logarithmic. That's right.
You didn't get rid of the log, you actually went towards the
No. No.
There are oscillars now that's posted on both sides.
Yeah. Yeah.
Vacuum.
That's what
But
we
at
have.
zero temperatures there's a phase diagram.
That's right.
So
Yeah.
the finite temperature phase diagram is kind of interesting.
Yeah. It could be interesting. I don't know. Okay.
So if I pick a super selection sector, sorry, if I pick a super selection sector of one winding,
Mm-hmm.
now I can quantize my theory in that super selection sector.
Okay.
Okay, and now the vacuum is the Z2 is broken in one side and Z2 is not broken on the other side. So isn't that what a phase transition is?
That's a clean distinction.
That's right. I just changed the words, but that's what it was, right?
So I don't want to talk about it like this because this is not the ground state. that's breaking your symmetry.
Particular
You
superselection
change the boundary conditions.
change
so
the
that
boundary
is
condition of the
also-
theory. I look at my
So
theory
eventually you will
particular
see that it's not going to, I'm not going to rely on your on the Z2 symmetry. I
You
will
may
lift
not,
it.
But is this correct?
So I am not going to commit to that, okay, because I haven't thought about it in that way. To me, the way I look at it is like I'm looking at some behavior of excited states, and that's where I can tell the difference. If I was looking at just the ground state, I wouldn't be able to tell them. So.
Is there a sense in which you can sum over these vertices on the Higgs side to show that you are generating non-perturbating mass? I'm just trying to see the connection, not confinement.
So it will come later. So right now I didn't have to use it. The only thing that I used was that because I'm in 2 plus 1D, I can do a calculation on both sides. And what did I use confinement for? I used it to get rid of all the symmetry reasons to have a phase transition. Okay, so that was the
but
use.
Now with these vertices, you can also check if there is any mass generation due to sum over these vertices. Like Polyakov. I'm saying that is there a connection between these vertices and what you said about confinement?
I don't think these vortices are going to exist. So if I didn't have Polyakov confinement, if I didn't UV complete the theory, I don't think this would generate any mass for the photon.
Yeah.
Okay.
Just in this situation where you have embedded U1 into SU2, let's say, where you have done that, in that case, if you sum over this solution, these are some particular.
So why would I care in that case? Yeah, go ahead.
I'm just trying to interpret it as a confinement. I would say that is a confinement. So it's a
Yeah.
All this stuff you didn't have monopoles.
For now, I didn't use them at all.
You didn't use them at all.
At all.
This works
The,
for
the, yeah, the only thing.
But the R.
The only thing I use them for is to get rid of the symmetry reasons to have a phase transition. So I got rid of the U1 topological symmetry, I got rid of the massless photon on one side, and so on and so forth, right? So I got rid of the massless photon on this side using that thing. Okay.
I mean, her point is that if you didn't have the monopoles, you don't have to do any work. There's obviously.
Right, right.
So what do you talk about? But this story survives the monopoles also.
Yeah, it will. That hopefully I'll come to. Not only that, it's actually going to rely. Eventually, if you break the Z2 symmetry, you will have to rely on the fact that you have monopoles to show that there is a phase transition. Yeah, but hopefully I'll get to that. I don't know.
So what I'm saying is that if you look at the vacuum of the theory, where phi winds once, and in that vacuum you quantize the theory.
So that's not. Is that a vacuum? I mean,
Yeah.
Define it.
I'm defining that to be a vacuum. Because
Okay.
you cannot now move around. Once you're there, you're stuck,
okay.
right? So in that super selection sector, if I look at the spectrum of the states, then the Z2 symmetry is spontaneously broken on one side, while it doesn't seem to be spontaneously broken on the other side. So in that super selection, I can distinguish this on symmetry level.
Yeah,
Seems
sounds right.
Maybe, yeah.
I see.
Is it? Are there other examples where you know that people do that, or?
no. Maybe.
Okay. Usually, a lot of people cringe when I say that I'm using the properties of an excited states to tell the difference between the two sides, but this is something we're claiming that that's going to that's a new way of finding out about phase transitions. Does not sort of fit in the usual story of looking at only ground state properties.
It's not even really an excited state, right? Because it has infinite energy. I mean, it's some deformation of the theory.
Right.
Right? I mean, in your path integral, you force this vortex to exist.
Mm-hmm.
So that's a modified theory.
Right.
And Abhijit's talking about that modified theory. Sounds totally reasonable.
Yeah, it's like a single kink versus
Single
no
kink.
kink.
Yes.
So single kink is of course an excited state
Mhm.
because it's but you're forcing it by saying that the spin here is -1
Mhm.
and the spin here is +1. So then it can only be this that single kink is the lowest energy.
Uh-huh.
So it's an excited state compared to no kink.
Right, right, right.
But it's a vacuum of that.
Yeah, but I'm making no. But
because on the standard vacuum you cannot even, as Shiraz was saying, this is infinite energy. So it's not
no. So this is the claim I'm making.
There will be smaller excited states on the non.
No. So this.
But this is totally different theory.
No. It's not. That's the claim. The claim is that you can use this fact that there is difference on the two sides. If you looked at what you call a deformation of the theory, it's telling you something about the ground state. So it's telling you that even if you didn't have any kind of vortices, okay, you were going from a uniform ground state from one side to the other, there's still a phase transition, and you can detect it using this. Okay, so it's not just a statement about a deformation.
You are going to the vortex solution.
Sorry?
In order to detect it, you are going
It's
to vortex.
an order parameter, but it doesn't mean that there is no phase transition. I'm just saying that there is a phase transition. This is one way to detect it. But if you could detect it this way, this means that even your ground state has a phase transition, going from one side to the other.
Will have a phase transition.
Sorry?
Okay, fine. I don't quite understand what's that ground state will have phase transition.
So, okay. What I mean is that if you computed, for example, if you computed your free energy,
Yes.
pressure, stuff like that, okay? So you expand about your ground state in that case, right? When you compute that. And I'm just saying that there's going to be non-analyticity in that case.
When
You don't have
energy, let's say,
Yes.
would you include the sectors with the vortices in them?
Yes.
Yeah.
So I will, for example, I will not necessarily include infinite energy states, but I can include vortex loops, which are not infinite energy states, right? So they are going to contribute to your path integral, even for a uniform state, because they are excitations of your system, finite energy excitations. So they should correspond to some kind of non-analyticity.
Even then you will see.
Right. So it doesn't necessarily depend on you looking at infinite energy states. You could look at like vortex loops, as I mean Shiraz was also pointing out yesterday. So, okay. So now there's another thing. So first thing to note is that I have shown that there is a gauge invariant probe that can tell the difference between Higgs and confinement. Okay. It changes sharply as I go from Higgs to confinement. The derivative of the Wilson loop expectation with respect to charge mass is going to be discontinuous. And the question is, can we verify that this coincides with a phase transition? Okay. So in general, it's hard, but you can do it in 2+1 dimensions. So you can tune parameters.
So,
Go ahead.
about what you said about doing a path integral, computing the free energy, and including even the loops which are finite energy. So now in this path integral, would you not be required to include these infinite vortex strings, or you can choose your path integral?
They have infinite.
Yeah, they have.
Not compute matches.
Yeah, so if I were to compute, an exponential, a path integral, like finite temperature path integral, you'll have exponential of minus beta e, and e is infinite. So you would think that
Can't you have a pair of one vortex on anti-vortex?
that's what I was telling him, that if you could make a vortex loop, that doesn't cost you infinite energy, and that could. Yes.
But as it becomes larger and larger, it costs more and more.
Right.
So in that sense, what I said does not quite translate to non-analyticity of the free energy.
Right. That's right. So, okay. Yeah, so I really wanted to point out that although we are looking at what is happening for what looks like excited states or infinite energy states, I'm really making a comment about what's happening when you're expanding about the ground state. Okay. So it turns out I can actually show that the jump in the holonomy or Wilson loop corresponds to a phase transition. And this I can do in 2+1 dimensions. So I can tune my parameters like the charge mass, lambda phi to the 4, and so on, to drive my theory into a weakly coupled regime where I can show that there is a first order phase transition. between Higgs and the confining sites.
You can
Okay.
compute it all the way to the phase transition.
Yeah, this is the first order transition that you can do, and it's an analog of the Coleman-Weinberg thing. Okay.
I'm not understanding. I mean, I would imagine that the transition happens where both the deeply Higgs calculation and the
Right. So you have to somehow be able to drive this transition for large enough MC squared, and it's possible to do it in 2 + 1. Okay.
and
Change
for-
something else.
So it's happening somewhere here that you can.
You're going to tell us that.
Hopefully, let's see. Okay, I have stuff. I can.
So
Well,
there's
I can.
something else you change so that it happens that way.
Right. So, if you're familiar, for example, with the Coleman-Weinberg in 4 dimensions. So, Coleman-Weinberg is the ordinary abelian Higgs. Okay. So there how do you tell that there is a phase transition, and what kind of phase transition do you have? So when you do it in 4 dimensions, okay, there are terms that you can write. So you can write phi to the phi square and phi to the 4 terms. This is what is marginally relevant, and you don't write higher order terms. So if you were to cook up a potential using these fields, the only thing you can get is something like this or something like that, okay? Because that's the potential that you have. So just by looking at this, you can't say whether the transition is, what happens right at the transition or what order this is, okay? So, however, what you can do is compute one-loop corrections to this, which is what Coleman and Weinberg did in their paper. And what you can see is that there is a log term, okay, that depends on phi, okay? And if you put that in, what you will see, so this is basically quantum corrections coming from the fact that these phi is coupled to electromagnetic field. So there is E squared here. And so when you have this log term, then you can have a potential that can be something like this.
So this is this fluctuation in this first order.
Yes, that's what I'm talking about. So once you do that, you can show that there's a first order phase transition in 4 dimensions when you do the abelian Higgs, and then things are under control, and so you go from something like this to something like this, and that's a first order transition. Now the good thing about 2 + 1 dimension is that you don't have to do a quantum correction. Now you can write down marginal operators that are phi to the 6th, okay? So without writing down this term, you can already engineer a first order phase transition just by using the fact that you have phi to the 6th term, okay?
And we've been a bit fast. I mean, the phi to the 6 has beta function and so on.
I've lost this part.
I can show you in detail tomorrow, okay? But basically, I am driving this to a part of the parameter space where I have control, and I can show that there's a first order phase transition, okay?
Yeah.
So it's a part of the parameter space, okay?
So just to understand, so the theory you're starting with in UV
Yes.
is free phi, then deformed by a bunch of operators which are either marginal or relevant.
Mm-hmm.
The relevant operators are phi squared, phi to the 4th, and the gauge number.
Right.
Now, what about this phi to the 6th? Isn't that irrelevant around that UV fixed point?
What do you mean?
When you compute the beta function, doesn't it?
Marginally irrelevant.
Yeah.
I don't think so. This is in 3 dimensions, right?
Yes.
So if you could write phi to the 4 in 4 dimensions and get it.
Phi to the 4 is also marginally irrelevant in 4 dimensions.
Right.
I thought it was similar in 3 dimensions. Phi to the 6 is marginally irrelevant.
That's okay. So you could.
So
This drives a phase transition in 4
I'm just trying
dimensions,
to
right?
understand what so the data of your UV theory
Yes.
is a free theory with 3-dimension full parameters.
Right.
A mass square, a phi to the 4.
You could do that. So that's what is required if I want to show, for example, that there is a regime where the jump in the Wilson loop corresponds to a phase transition.
But just to understand.
If I wanted to do that.
Wait, the theory is defined by 3-dimension full parameters.
Mm-hmm.
Now,
Yes.
in the space of 3-dimension full parameters, the 2 ratios, you will have to play around
Yes.
with.
And
you can't invoke a 3rd parameter, which is the coefficient of the phi to the 6, because it doesn't appear in the UV definition of the theory.
No. I'm saying that you could change the UV definition of the theory.
I'm saying there's no if my memory is correct that this 5 plus 6 is marginally irrelevant, then there is no UV theory with a new parameter associated with 5 plus 6. The set of RG flows away from the free theory is three parameter dimensionful numbers or 2 parameter set of flows. There isn't a third parameter set of flows. So you shouldn't need to tune 3-dimensionless parameters to do what you're doing, is what I'm saying. If my memory is correct, which very likely is wrong.
So I know that I don't
know what happens to the beta function with the gauge.
She's going to talk about it next time. No, sorry. Yes.
Yeah.
Okay.
Yeah.
So I know that
Yeah.
Gauge optimization.
If you're going to talk about it next time, maybe we have again detail.
Okay. So anyway, the transition coincides with a jump in the holonomy right there, and this reinforces the belief that the transition would persist to coincide with a change in the holonomy when stuff is strongly coupled. Okay. So this is a little bit of a summary.
Sorry.
Go ahead.
The argument with 5-6 doesn't rely on gauge. It's just like if the coefficient of 5-4 is negative, then 5-6 can give you this kind of a free energy.
Yeah.
Right.
No, but the question is, can you turn on a 5-6 in a UV complete?
Shiraz is thinking we usually don't find
Right. Okay. So this is sort of the summary of what I discussed over 2 days. So I showed that there's a physically interesting situation. There are physically interesting situations where Higgs and confinement phases can be sharply distinct. This requires the Higgs field to be charged under U1 global symmetry, and this is naturally satisfied by QCD.
What is this last comment? It's naturally satisfied.
Yeah, I mean this is what my original motivation was, right?
Meaning as an analogy.
Yeah.
Okay.
Yeah.
But that's a zero difference.
Yes. There is a global symmetry in QCD, which is the barrier number symmetry. That's all I'm talking about here.
This is the 3-flavor, 3-color
Yeah.
model.
Yeah.
The U1 part of that flavor.
Yep. So maybe what I'm going to show tomorrow is that the flavor permutation symmetry is not crucial to actually argue for what I argued today. And then what's interesting, one thing would be interesting to do is to gauge the global symmetry that we have. And so that would regulate the logarithmic divergence of the vortices and would allow me to use a lot of the language that people use for topological order and stuff like that. So that's, I would end it today here, yeah.